Good afternoon, everybody. Thank you for being here. Welcome to our December installment of ENERCALC Office Hours. As most of you guys know, obviously by now, we've transitioned from sessions to Zoom, and we have just a couple of quick housekeeping items before we start our program for today. So before we get going, I want to just start with a quick sound check. If you direct your attention to the bottom menu of your Zoom window, either in your browser or on your desktop, you'll see the chat tool, and you also have your reaction emojis. So if you're able to hear me right now, just go ahead and give us a thumbs up emoji in the chat, or you can throw us a raised hand, a thumbs up, applause, what have you. Perfect. Thank you guys for confirming that. And then before we get going on the rest of our housekeeping items, we also want to go ahead and do a sound check for our primary speaker for today. So once again, in just a moment, if you can hear Chelsea's voice, go ahead and throw us a thumbs up reaction as well.
Hey everybody, this is Chelsea. If you can hear me, then that's good.
All right. Thank you guys very much for helping us with that. Now that we have our tech checks out of the way, we are going to go ahead and disable the chat, and we'll move on to some introductions and get going with today's program. If you have any questions for our session today, we do have the Q&A dialogue that I'll get to in a moment. So my name is Seth Rosearm. I'm a senior structural engineer and software developer here at ENERCALC. Our presenter for today's ENERCALC Office Hours program is Chelsea Darnell-Zhang. Chelsea's a product engineer here at ENERCALC, and she kind of splits her time between technical training for ENERCALC customers, working with the engineering team here at ENERCALC on specifications and technical behavior of our software, and then offering customer support to our users and helping maintain national and regional presence for ENERCALC at various industry events. Prior to joining ENERCALC, October of this year, Chelsea was an engineer at a structural engineering firm in the San Francisco Bay Area. She worked on a lot of different projects from high-end residential to elementary schools, seismic retrofit, a variety of different project types. She's also an active member in the SEOC Pathways program for advancing structural engineering in California by improving recruitment and retention representation for underrepresented groups in the profession. So for anybody who's new here this month, ENERCALC Office Hours is a time for us to connect with customers. And we do multiple different things. We showcase new features and updates from ENERCALC. We go over optimized design workflows. We answer questions that are submitted by customers in advance of the sessions. We do open Q&A and go through hands-on examples. And then we also do deep dives on various features for specific ENERCALC modules. So if there's any question that's too involved or requires deeper digging and research, that'll be a better fit for reaching out to our support team because they can investigate and kind of break down your question and get you answers to those. As a minor point of order, you will notice everybody's microphones are muted just to make sure we don't get any echo or feedback. As I mentioned, we do have open Q&A at the end of every session. If you want to submit a question for today's Q&A, just use that dialogue in the lower dashboard of your window. If you experience any audio problems at any point during the session, you can simply refresh your browser, close out and rejoin the session. If you want to rewatch today's program, any of our previous programs, or share those with someone on your engineering team, all those recordings are posted to the Office Hours playlist on our ENERCALC YouTube channel. And I believe there's also a redirect under the For Our Users page on our website. With that, I will go ahead and hand it over to Chelsea to get going on our program for today.
Okay, hello everybody. Looks like we have a good turnout today, so thanks for being here. And thanks, Seth, for that introduction. So welcome to another session of our monthly Office Hours program. As I said, I'm Chelsea, and I'm excited to be presenting to you all today. So I'd like to start off with a brief overview of our overall agenda. Today, we're going to be covering ENERCALC's latest build. We'll talk about some new features and functions in ENERCALC. We'll go through a general foundation design example using the general footing module in ENERCALC. We'll talk about how you can get registered for these office hours so that you get notified. And then at the end, we'll have a live Q&A. So as that said, please feel free to drop your questions in the Q&A form throughout the presentation. So first, we'd like to encourage you all to check your software to make sure that you are on the latest build of ENERCALC. So if you could all take a minute, you can open up your software and you can see your build number here at the top. And the current build as of today is 2024-1202. So we do release monthly updates, and we want to make sure that our users are taking advantage of the newest features and capabilities of the program. This is important because we commonly receive support questions from users where a user notes that maybe they don't see a certain feature or maybe their hand calculation isn't matching the program output. And very often we can resolve these issues by identifying that the user is just on an old build. And once they update, that gets resolved. So because this is important, we're going to quickly show you how to update your build and how you can get notifications for new builds so that you can always make sure that you're staying up to date. So at the top of your program, there's this update button in the upper ribbon. And if we go ahead and click that, it opens up this window and you're able to check for updates now. You can also click to launch our For Our Users page. And once we click that button, this opens up our For Our Users page where you can scroll down to the software downloads and install instructions section. And if you click this build updater, if you currently have ENERCALC installed on your computer, then this will download the latest version. And once you click and download this, you'll be running the latest and greatest version of ENERCALC. So if you'd like for the program to automatically check for updates at your startup, you can select this checkbox down here below. And a quick note on this checkbox, the feature here for users on build 2023-0830 to 2024-0228, so that's the August 2023 through February 2024 builds. This feature to notify you of the availability of new updates is not functioning properly. So if you're affected by this, you'll need to update manually one time. You can do this by clicking here and downloading from our ENERCALC webpage. And once you do that, you should be able to click this. And then from then on, you'll be getting the updates automatically. Now, if you'd prefer to be notified of the latest ENERCALC updates by email instead, you can scan this QR code here, or you can go to enercalc.com/updates emails, and you can fill out your contact information here, and then you'll receive those notifications via email. So if you've not been on the latest build, or maybe you haven't had time recently to poke around in ENERCALC, we just wanted to highlight some of the newer features and functions that we hope that you all can take advantage of. So first, we want to discuss the decoupling of the IBC and ASC editions. So we started noticing that some jurisdictions were mixing and matching design standards. So for example, you might have a jurisdiction who is on IBC 2015, which references ASC 710, but they would like to use IBC 2015 with ASC 716. So before, ENERCALC lumped the ASC edition up here under the IBC that referenced it. So for example, if you were in IBC 2015, you'd see ASC 710 here next to it, and you'd be forced to use the ASC edition referenced by the specific IBC. But now after we've decoupled the IBC and ASC editions, you can use whatever IBC and ASCE combination works for you. So you have a little bit more flexibility to meet your jurisdiction's requirements. Now, the next update that we wanted to talk about is the addition of new ASC 722 modules. So you might have noticed that we started adding 3 new tabs to our calculation menu. So this first tab here is the seismic loads tab, and we added calculation modules for seismic base shear, wall anchorage, and seismic demands on non-structural components. And this one here is actually brand new. It was part of our 1202 build, so make sure you're updated so you can take advantage of that. And then the next tab is our wind loads tab, and we added calculation modules for Chapter 27 directional procedure, Chapter 28 envelope procedure, and wind enclosure. And then a module for components and cladding per Chapter 30 is in active development, and it'll live here once it's been released. So again, make sure you're staying up to date with the latest builds so you can use that once it's live. And then the final tab is our other loads tab. We have a calculation module right now for live load reduction, and then additional calculation modules such as snow loads will be living here once they've been released. So the third exciting update that we want to talk about is native load linking within ENERCALC. So hopefully this is familiar to some of you, but if it's not, load linking gives the user the ability to automatically link reactions from one calculation to another, and the ability to change something in one member and then have those changes trickle down to all the supporting members. So this was one of our most requested features from our users, and we're excited to say that load linking for steel beams is here and it's ready for your use. So load linking for other modules is also in development. So again, make sure you're staying up to date with the latest builds, and then you can use those new features once they roll out. So I want to just take a quick moment to look at load linking. If you are in the latest build, you'll see this new tab up here called Calc Order. This tab is going to organize all your calculations based on load path order. So you can have a quick overview of calculations that are linked to each other in the order that the load is distributed and not necessarily the order that you created the calculation. So you can link multiple reactions from multiple members at the same time, and ENERCALC is going to understand the load path logic and ensure that all calculations are performed in the order that they should be. And then at the bottom of our screen, we can see these load linking status badges. So these are going to help you navigate the status of each calculation and understand the warnings better. So for example, if we were to update our beam number 1, we'd see that the linked calculations would turn from green to orange and red, indicating that a recalc is needed because these calculations are out of date. And we can do this by clicking this new Recalculate Linked Loads button. Up here, if we click this, it'll allow us to bulk recalculate all of the calculations to ensure that the most up-to-date reactions are being used and that their effects are trickling down to all the related members downstream. So I just want to jump into a steel beam calculation module real quick. If we're in a steel beam calculation module, we can see this new tab called Linked Loads. And in this tab, we can grab reactions from whatever calculations we have in our ENERCALC project file, and then apply them to our current beam that we're working on. And as we cycle through these calculations, we'll get to see this 2D diagram representation of the member that you're looking at to help refresh your memory. And this can help give you some confidence that you're choosing the correct member to link. And then once you've picked a member to link and you go and select a reaction, you can determine how you want the reactions to be applied to your current member. So for example, you could choose to apply linked loads at midspan, third points, quarter points, a specific spacing, or a specific location. And then all of your linked reactions are going to be down here. And you'll also see any linked reaction is going to be blue in your 2D diagram over here. So overall, load linking is a powerful tool, and it allows engineers to create a well-connected chain of calculations while minimizing the risk of transcription errors. So no more, writing down your reactions on a piece of paper or making your own Excel spreadsheet for them. Everything is now just within ENERCALC. And if you would like more information on load linking, we encourage you to check out our load linking playlist on our YouTube channel. And so this playlist is going to walk you through load linking step by step so that you can start to leverage this powerful tool. And now the final feature that we wanted to highlight today is our ENERCALC for Revit Gravity Full Load Path. So if you attended last month's office hour session, Seth took us through ENERCALC for Revit, which is a Revit plugin that allows you to leverage ENERCALC SEL to design structural members fully within Revit without having to export information to another calculation software. So ENERCALC for Revit previously supported steel beam, steel composite beam, wood beam, and girders. And now it also supports steel columns and general foundations. So this completes the gravity load path for a steel structural member. So let's take a minute to watch this in action. So here we have our Revit model, and we can navigate up to the ENERCALC SEL ribbon, and we can select column design. And then we can pick our steel column that we want to design. We can confirm our gravity support conditions. We can confirm our slenderness inputs in both the X and Y directions. We can indicate if any elements are bracing our column that we're designing. We can confirm tributary loads. And then once everything looks good and we click OK, the program's going to open up an ENERCALC calculation. And all of the information from Revit is going to be pre-populated. And so this will include your column size from Revit. It'll include applied loads that are coming in from Revit. You'll also see like column geometry, column height will be included in here. And once we go through this calculation, we like what we see, everything's working well. We can click save and close, and we'll be taken back to Revit. And we can see that our column size will automatically be adjusted to match our current calculation. And then we can use the same point and click logic for the foundation. So you can hop in here, you can make any adjustments to your design parameters you need to. You can see the loads that are coming in from Revit. You can update your footing geometry and your reinforcement information as needed. And then once we click save and close, we'll see that those changes are going to get carried over into our Revit model. So our footing size is automatically updated to match our calculation. We have reinforcement information here in Revit. And so we have this like seamless conversation between Revit and ENERCALC SEL. And so if you have an ENERCALC for Revit license, you can go to our For Our Users page, and below the update for ENERCALC SEL, you can install the latest version of ENERCALC for Revit, so you can start to leverage the full gravity load path for steel members. So moving on, the focus of our session today is going to be the design of general foundations using the general footing module in ENERCALC. So we're going to cover this module's capabilities and limitations by walking through an example together. So here's just a quick overview of the capabilities and features of the general footing module. So the best use of the general footing module is for the analysis and design of rectangular footings with applied axial overburden, moment, and shear loads. And this module is going to allow the user to choose to perform or not perform biaxial analysis as needed. And this module will also check soil bearing pressure, overturning stability, sliding stability for service level demands, as well as flexure, one-way shear, and two-way shear for LRFD level demands. So for today's example, we're going to pretend that we've been asked to design a rectangular pad footing to support a steel column, and our steel base plate is going to sit on a 12-inch square, 6-inch tall pedestal, and we've determined these applied loads. And our design is going to be based on IBC 2021 and ACI 31819. And I'll be mentioning some differences between ACI 31819 and ACI 31814 as they come up. So let's jump into our ENERCALC program. We can start a new footing calculation by clicking Add, navigating to the Foundations tab, and then clicking our General Footing module. And then we're going to start with our inputs in our General tab, and we'll be working our way from left to right through our inputs to set up our calculation. And so here on our General tab, we can give our calculation a unique name, and then we can jump into filling out all of our inputs down here. So before diving into these inputs, I do want to mention that throughout today's example, I'm going to be referencing default values. So as some of you know, ENERCALC does allow users to set default values for various parameters, such as F prime C, Fy, and phi values. And if you're following along in your program, you might notice that some of your default values might differ from some of the ones I'm showing. So it's just always good to double check that the defaults that you have in your program are applicable to your current calculation. And if for any reason you'd like to modify your default values, you can always do this in the Settings tab. And if you need a refresher on this process for modifying your default values, Mac did walk through this in detail in July's office hours presentation, and you can find this on our office hours page. And if you pop into this July presentation, the default values example is going to start at 1625. So check that out if you need some help updating your values. But jumping back to our example, we can see here that 3000 PSI concrete and 60 KSI rebar is provided as my default material properties. And of course, as the engineer, you can verify if these are appropriate or you can update them as required. But for our example, I like these and I'm going to move on to my next input. So for concrete modulus, the user can either manually input a value here, or they can use one of these buttons to calculate the concrete modulus based on the F prime C input that we have up here. So to save myself some time and the effort of grabbing my calculator, I'm going to use this far left button to calculate my concrete modulus. And then moving on, we can see I have some more defaults here. As the engineer, it's always good to just come in and verify that these are still appropriate for your project. I would like to note that since code modifications for lightweight concrete are not applied in this module, the purpose of this concrete density input is to mainly allow the user to specify something between the 145 to 150 pounds per cubic foot range. So just keep that in mind when you're updating this. And continuing with our example, I like these default values, so I'm going to move on to my analysis and design settings. So as I mentioned before, this module allows the user to choose to perform or not perform biaxial analysis as needed. And because biaxial analysis involves a lot of iterative calculations, rerunning the entire analysis and design every time we tweak an input would be inefficient for the program. So if we were to choose to run biaxial analysis, we'd see that the program would automatically switch to manual recalculation mode. And we'd notice that we have this click to calculate button that appears in the top right-hand corner. So anytime you change an input, the program is going to prompt you to manually recalculate by clicking this button. And also when biaxial analysis is selected, an additional input is going to appear here below. And this input is going to specify the fraction as a decimal of the footing dimension from the edge to use when calculating moments and shears. So that means a smaller value here is going to result in a more conservative design because it's going to focus on a narrower strip where soil bearing pressure is going to be the highest. So for example, if I was going to input a value of 1.0 here, I would be telling the program to base the calculation on the average pressure along the entire footing edge. While if I was going to put a value of 0.1 here, I would be telling the program to focus on the average pressure along the most heavily loaded 10%. So you can toggle this up and down and use your engineering judgment to decide the soil pressure that is best to use for your design. But for today's example, we're going to keep it simple. We are going to select no for biaxial analysis, and we're going to move on. So next up, we have the option to select or deselect some settings. The first is regarding checks for sliding. So we can check this box if we would like to ignore sliding for any reason. For example, maybe we have an attached slab that we want to use for sliding resistance. For example, we're going to keep this unchecked. And then the next box is for footing weights to be considered for soil bearing pressure. So when this box is selected, the module is going to calculate the self weight of the footing and apply as a downward load when determining soil bearing pressures. And the self weight is going to be multiplied by the dead load factor in each of the soil bearing pressure load combinations. Now, I'd like to note that this option here should generally be selected because deselecting this option can lead to incorrect bearing pressure calculations in footings with moment. So you might be considering deselecting this because maybe you're trying to compare soil bearing pressures to net allowable pressures. But if you wanted to do this, it would be better to use the option on the soil allowables tab to increase bearing by footing weight instead, or to adjust your allowable bearing pressure manually if your design warranted further adjustments. So we'll mention that again when we jump to the soil allowables tab, but just good to be aware this box should generally be selected. And then the next checkbox is for the footing weights to be considered for sliding, overturning, and uplift. So again, when this box is selected, the module is going to calculate the self weight of the footing and apply it as a downward load when determining sliding, overturning, and uplift. And again, the self weight is going to be multiplied by the dead load factor in each of these stability load combinations. So next up is our minimum flexural steel ratio. You can see that our default value here of 0.0018 per ACI 7611 is already included. I would like to point out that this minimum ratio is for flexural steel. This is not a minimum ratio for temperature and shrinkage steel. So this means if your footing has net uplift and you needed to provide both a top and a bottom mat of reinforcement, this ratio would apply to the area of steel provided in both the top and bottom mat. So this is not something that can be shared between the top and bottom mats like temperature and shrinkage steel. And this is explained further in the commentary in ACI shown here. So moving on to our safety factor inputs, you can see my default safety factor here is 1. Of course, you can revise this if you'd like to, but I like these, so I'm going to keep them. Now, if your design is based on the requirements of ACI 31814, you will see an additional minimum reinforcing check here in the general tab. And ACI 31819 has clarified that the calculation of minimum flexural steel for footings is based on 0.0018 and not sections 9612 or 9613. So the option to consider these sections is removed when your governing code is set to IBC 2021 or later. Okay, our last input on the general tab. This is for the selection to reduce overturning effects per ASCE 7, section 1213.4. For our example, we're going to leave this unchecked, but it's always good to pop in here and see if you meet any of these conditions so that you can take advantage of that overturning effect reduction. Okay, moving on to our next tab. We're going to define our soil allowables inputs here. So first up, we have our allowable bearing pressure, and we can either manually input an allowable bearing pressure here, or we can use this sweet presumptive values from IBC button over here to select a value from table 1806.2. And for our example, I'm going to click this button and select 2 KSF. And then next, we're going to confirm or revise our soil density and define the depth of our footing base below the surface of the soil. For this example, I'm happy with our default density, but you might be able to revise this based on information from your geotech report. And then for footing depth below soil surface, I'm going to start with my footing at 1 foot below. So next, we can confirm or revise our passive resistance and friction coefficient. So one thing to note here is that the sliding resistance due to passive pressure is going to be added to the sliding resistance due to friction to determine the total resistance to sliding for each load combination. So if your geotech report has any limitations on using both passive and friction resistance together, you would have to adjust these values to satisfy those geotechnical requirements. But surprise, for this example, I am happy with these defaults. So moving on to the soil bearing increase section, this section is going to allow you to specify dimensions that, if exceeded, will automatically increase the allowable soil bearing pressure. So I'd like to pause on our steel column foundation example for just a minute so we can take some time to dive into each of these inputs so we can understand what ENERCALC would do with information that we entered in here. So let's look at increases based on footing depth first. I think it'll be easiest to explain these inputs with a quick hypothetical scenario. So we're going to say that our geotechnical report states that a 0.15 KSF increase in bearing pressure is allowed for each foot of depth when the base is deeper than 4 feet below the top of soil. And we're going to say that we have a footing base that is 6 feet below the top of soil. And our allowable bearing pressure we entered up here is 3 KSF. So once we input the parameters from our geotech here, we'll see that our allowable bearing pressure increases from 3 KSF to 3.3 KSF. And then next we can look at increases based on footing plan dimension. So again, we're going to look at these with a quick hypothetical scenario. We're going to say that our geotechnical report states that, again, we get a 0.15 KSF increase, but this time it's when it's allowed for each foot when the largest plan dimension of the footing is greater than 4 feet. And we're going to say that we have a 12 foot by 6 foot footing. So our largest plan dimension is this 12 feet. So once we input our geotechnical parameters here, we'll see that we increase from 3 KSF up to 4.2 KSF. Now, one thing to note here is that the increases based on footing depth and footing plan dimensions are going to be cumulative. So if we have our 12 foot by 6 foot wide, 6 foot deep footing with our previously mentioned increases for our geotechnical report, we're going to see that our adjusted allowable bearing pressure increases from 3 KSF up to 4.5 KSF. And we would expect that if our geotechnical report allowed some increases based on footing depth or footing plan dimension, the geotech would also specify some maximum allowed bearing pressure. So we can input that value over here. And this is going to be our upper limit on the soil bearing pressure that will not be exceeded regardless of the increases that we specify over here in this section. So jumping back to our steel column foundation example, we are actually going to assume that we do not have a geotechnical report. So we'll be leaving this section blank and we're going to move on. And now the last input on this tab is the checkbox for increasing bearing by footing weight. Now this is what we mentioned during the general tabs input. You might want to select this if you're trying to compare soil bearing pressures to net allowable pressures. So when you select this box, the module is going to calculate the weight of 1 square foot of footing, and it'll add it to the allowable soil bearing value. And this adjustment is going to prevent the soil from being penalized for the footing self-weight, which could be useful when the geotechnical report provides allowable net bearing pressures. But as I said before, we don't have a geotech report, so we're going to have to leave this one unchecked. And then moving on to the next tab, we can see I have some default values here for footing dimensions. I'm actually going to leave most of these defaults alone for now because I would like to input my loads and then come back and use this AutoCalc footing size and thickness button. But before we jump into that, I want to input our pedestal dimensions in here. So we go ahead and we input our pedestal dimensions, and then we can specify whether the self-weight of the pedestal should be considered when determining soil bearing pressure and when performing checks for sliding, overturning, and uplift. Now, this pedestal weight is only going to be determined if there's a non-zero input here for the pedestal height. So one reason a user might choose to specify pedestal plan dimensions, but no height, is because maybe they want to define the critical locations for ENERCALC to check shear and flexure. So ENERCALC is going to assume that the critical location is the face of the pedestal we defined. So if you have a different type of supporting member, you might have to manually adjust your pedestal plan dimensions to satisfy the requirements of this ACI table. And if you do not input any pedestal plan dimensions, then the load location will be treated as the face of the pedestal when determining these critical locations. So now that we've defined our pedestal dimensions, we're going to put a pin in this tab and we're going to jump over to our applied loads. So the applied loads tab has some purple notes here and some reference images down at the bottom to help the user confirm their load inputs. So we see here that a positive axial input is going to result in a downward force on the footing, and positive moments and shear inputs will result in higher pressures along the positive X and positive Z edges of the footing. And then it's also noted here that shear is going to be applied at the top of the pedestal. So if you have a non-zero pedestal height, this will result in an additional moment applied to the top of your footing. So let's go ahead and enter our applied loads. And it's important to note here that any overburden loads are going to be emitted from the area that we defined as the pedestal plan dimensions, regardless of if we have a pedestal height defined or not. So since we have a 12-inch square pedestal, the overburden load is going to be omitted from this area. Now, below the allowable loads table, there's this checkbox here to include soil weight over footing. So when this box is selected, the weight of the soil will be added to the dead load. And it's important to note here again that the area of the pedestal is going to be excluded from the soil weight calculation. And we also see a warning below the applied loads table noting that moments and shears are not applied about axes simultaneously. So this is reminding us that we chose to not run biaxial analysis. And if we were to hop back to our general tab and select yes here, we would see that these notes would be removed. So jumping to the next tab, load combinations. This tab is hopefully quite familiar to all of you. This is a pretty consistent tab throughout all of ENERCALC modules, so we're not going to spend a lot of time here. But I do want to point out that the load combinations in the LRFD tab are going to be used to calculate moments and shears in the footing for use in determining stresses and required reinforcing. And the combinations on this tab are going to be at the strength level. And then the load combinations in the other two tabs are going to be at the service level, and they'll be used for checking soil bearing pressure and sliding and overturning stability. So now that we have our applied loads and we're happy with our load combinations, I want to jump back into our footing data tab. So for this example, we don't really have too many restrictions on footing size and footing depth. So instead of manually inputting width and length dimensions, I want to use our nifty AutoCalc footing size and thickness button down here. So when we click this button, it opens up this menu and we can see we have two options. We can choose a square or a rectangular footing shape. But before we do that, let's discuss these notes down here. So the AutoCalc footing size and thickness button is going to provide us with suggested footing dimensions to satisfy soil bearing pressure and overturning, as well as a suggested footing thickness to satisfy 1- and 2-way shear. But these recommended footing dimensions may not fully satisfy the requirements for flexure, uplift, sliding, or minimum reinforcement. So we might notice that after we run this auto calculation, we might need to adjust our footing dimensions and reinforcement inputs to make sure that all of our design checks are met. So back to our example, we're going to choose rectangular footing, and then let's see how quickly this AutoCalc button determines an appropriate footing size. So we click our button, choose rectangular, and bam, we have a footing design in just a few seconds. So I really like this feature. As a young engineer in design, I often struggled with not always knowing where to start when it came with determining footing size and depth. And this button provided a quick solution. It allowed me to arrive at a reasonable starting point with just one click, and it still gave me the flexibility to revise the footing as needed. Now, if you're still with me, you might have noticed that I said starting point and not final footing design. And that's because we still have a little bit of work to do here. So I want to take a look at our AutoCalc dimensions, and I just don't really love these. So I'm going to make some adjustments, and then I'm going to see if I can make these new dimensions work by adjusting my reinforcement. So we have our updated dimensions here, and then over to the right, we have all of our outputs. And we can see that we've satisfied most of our design checks, but we have not satisfied minimum reinforcement or one of our one-way shear checks. So let's revise our rebar inputs here, and let's see if we can resolve these. So we update our reinforcement to 4 number 5 bars parallel to XX and 7 number 5 bars parallel to ZZ. And then we confirm our edge clear cover down here. And we can see that we're now satisfying all of our design checks and our footing design is complete. Now, before we move on to our results tab, you might have noticed that this bandwidth distribution check appeared in our window when we selected a rectangular footing design. And this check references ACI section 13333. And this section requires a higher percentage of the reinforcement to be concentrated in a strip of footing closer to the applied load. So we're not going to dive too deep into this check today, but it is important to note that the engineer should confirm that their detailing does satisfy this ACI requirement when they have a rectangular footing. Okay, so now we have a design that works, and we're going to go through the output side of the screen. We're going to start with our results tab. So here we have a general overview of all the design checks that the module has done to verify our footing design, and we'll dive into each of these in a little more detail as we navigate through the calculations tab. But first, let's discuss these two notes that have appeared here at the bottom. So first, we can see this red note here, and it's telling us that a top reinforcing mat is required. And if we pop open our bending tab over here to the left, we can see that since we have an applied seismic bending moment, we have tension in the top of the footing for one of our load combinations. So back when we specified our reinforcement in the footing data tab, we told the program what reinforcement we wanted for the bottom mat of our footing. Now, if there's tension on the top surface of our footing, ENERCALC is going to assume that the same number and size of bars is also provided as a top mat. And it's also going to assume that the same clear cover that the top clear cover is the same as the bottom clear cover that we specified. So we do understand that this is a limitation of this module, and it can be a little bit confusing for the user, and we are working on updates to improve this. But for now, it's important that you understand that if there is tension on the top of your footing, the program is going to assume that the top and bottom mat both match the inputs you specified here in the footing data tab. And if this assumption does not match your design intent, you might need to run some additional checks to confirm your design. And this note also serves to remind the user that since there's tension in the top of the footing, a hand calc is going to be required to check anchor pullout to verify that the anchors and our reinforcement connecting the column to the footing are adequate. So the next note we see here references ACI 31819 section 13262. And if you're familiar with the ACI 31819 updates, you know that ACI has added a new size effect factor here to the shear capacity equations. However, section 13262 states that for certain foundations, the size effect factor can be neglected. So ENERCALC takes advantage of this by setting the factor equal to 1.0 in the one-way and two-way shear calculation equations. Now, as we navigate from left to right in the calculations tab over here, we can see detailed design results for the various design checks that the program performs, starting with the soil pressures check, which compares the applied surface loads to the bearing pressure capacity for our soil below the footing for each load combination. Next, we have our overturning results, showing the detailed design results for the overturning stability checks. The demands here are going to be at service level. And in this tab, we have our sliding results, showing detailed design results for the sliding stability checks. Again, the demands here are going to be at service level. And as we discussed earlier, the sliding resistance due to passive pressure is going to be added to the sliding resistance due to friction to determine the total resistance to sliding for each load combination. Moving on, we can see detailed design results for the bending design. These calculations are going to compare LRFD level demands and capacities to confirm that the flexural reinforcement we specified is adequate. And one thing to note here is that the critical section is going to be the face of the pedestal we defined. And if we had no pedestal defined, then the critical section would be the location of the applied load. And then in our final calculations tab, our shear tab here, we can see detailed design results for our shear design. So similar to the bending tab, these calculations are going to compare LRFD level demands and capacities to confirm the footing depth and reinforcement provided is adequate. And for a one-way shear, the concrete weight modification factor and footing size factor are going to both assume to be 1.0. And the critical section is going to be D away from the face of the pedestal we defined. And again, if there is no pedestal defined, the critical section will be D away from the location of the applied load. And quick note here, if you were to toggle between ACI 31814 and ACI 31819 designs, you might notice that one-way shear capacity for footings is going to be lower in ACI 31819. And this is due to code updates in Chapter 22 and the new one-way shear equations. So in the shear tab, if we scroll over, we can see our two-way shear information, and the critical section for two-way shear is going to be D over 2 away from the face of the pedestal we defined. And again, if we don't have a pedestal defined, it'll be D over 2 away from the location of the applied load. And then one thing I just wanted to note here is that the punching shear demand, it's not going to be calculated using the full applied load on the footing, like you might do if you were doing a quick hand calc. Instead, the two-way shear calculation is going to exclude the portion of the load beneath the footing that's transferred through direct compression. So only the load from the soil pressure within this red highlighted area is actually going to be used in the two-way shear calculation. Okay, finally, we can pop over. We can look at our 2D diagram. We can see our footing size, pedestal information, rebar information. We can check out our 3D diagram, make sure our loads are looking good. And we have a beautiful completed footing design. So real quick, I wanted to mention that if you have a more complex footing, maybe you have like an irregularly shaped footing like this one, or a footing with up to 5 pedestals that falls outside of the capabilities of the general footing module, ENERCALC does offer a general footing by FEM module. Due to the complexity of finite element analysis, we're not going to cover it today, but if you ever encounter a limitation in the general footing module for your design, we do encourage you to check out the general footing by FEM module and see if this meets your needs. And then, of course, if you have any questions about this module, feel free to reach out to us at support@enercalc.com. Okay, before we dive into today's Q&A, I'd like to encourage you all to register for office hours to ensure that you're receiving notifications directly to your inbox. So oftentimes the email addresses that we have on file, they belong to like an IT department or an admin who's managing the office's licenses. So it means that notifications about these sessions might not be reaching the engineers who actually could benefit from them. So to avoid missing out, if you want to see more of what you saw today, I highly recommend that anyone interested register on our website, and you can receive updates directly, and then you can always unsubscribe in the future if you need to. So if you are interested, you can register by going to enercalc.com/office hours, or you can go to our website and click on For Our Users, select Get Help, and then navigate to our office hours page. This will take you to our registration page. You can input your contact information here, click Submit, and then you'll be on our email list. And also at the bottom, we regularly update the info regarding the next office hours session. So you can always come to our website here to check out what's coming up. And then at the same enercalc.com/office hours webpage, we also post all of the unedited recordings from the previous office hour sessions. So you can find these by scrolling down the page. And the last one that we posted was the ENERCALC for Revit session, which was held on November 13th. So if you missed that one, go check it out. All right, now it's time to open it up for some Q&A.
All right. Thanks, Chelsea. Let's go ahead and hit some Q&A here. So I'm going through our queue. We've got a lot of great questions. So let me just go ahead and throw one up for you here. So first question, kind of a clarifying question. For the pedestal load, shear is 5 kips, moment is 15 kip foot. Is that moment from the 5 kips shear? So a clarifying question about the nature of those applied loads. You can go ahead and jump back to that slide if you want to, and I'll kind of let you take it away. But my understanding is that you were applying those both as individual externally applied loads. we weren't explicitly linking those to each other, and they're certainly not linked to each other in the input in the interface. But you can go ahead and take that and run with it.
Yeah. So these are just like separate applied loads. In the, I mean, I drew a column and I put 5 kips at like 10 feet. So they're, linked in that way. But in the ENERCALC module, they are input separately, just as like loading applied at the top of the footing.
Right. And
So I
as
guess
go
I
ahead,
guess I
sorry.
could mention here, we have our 6-inch tall pedestal. So what we would actually see if we looked at our seismic load case is we would see our 15 kip feet, and then we would see an additional 5 kip times half a foot of shear loading in our ENERCALC calculation.
Yeah, that's a great point. That's what I was going to mention as well is
Okay.
all those horizontal shears are going to be applied at the top of the pedestal, and so you'll see additional induced moments as a result of those horizontal forces.
Yep.
Perfect. All right. Question about shear equations. What shear equation is being used for the one-way shear calculations?
Yes. Let's jump back to here. So for the one-way shear calculations, if we're in ACI 31814, we're going to use the pretty familiar just 2 lambda f prime c equation. But if we are in ACI 31819, then ENERCALC assumes that no shear reinforcement is provided in the footing. So we're going to be pushed to that equation C in our new table. So that's why we see that drop in shear capacity. Our reinforcement ratio is going to play a part here, and it's going to reduce our shear capacity.
Perfect. All right, moving down the list here. Question: can you design a foundation using the EFR intercalc for Revit integration? Can you elaborate on what the process looks like? So, yes, you definitely can do that. That process is already out in the wild for those of our customers who are using intercalc for Revit right now. The latest update does include both steel column integration and general foundation. So, the workflow is fundamentally just like the other intercalc for Revit workflows. That process starts in the Revit model. We launch a calculation by that point and click workflow that Chelsea was showing you guys earlier. Select the foundation you're interested in, and that brings a whole variety of information. Basically, is a real-time migration of all these inputs that Chelsea walked you guys through: footing geometry, footing thickness, soil properties, uh, the eccentricity between the applied loads and the footing center, all those properties in real time into your intercalc calculation. Interact with your calculation, make design decisions about your geometry, about your rebar parameters, reinforcement, so on and so forth, and then migrate all that information back in real time to your Revit model by hitting save and close in your calculation. So basically a more automated fast forward implementation of the same process that Chelsea walked you guys through today. Question from Pavel. If no pedestal is being defined, what critical parameter is being used for the two-way check?
Mm-hmm.
And I think you kind of touched on the answer to that one, but go ahead.
Yeah, we can look at that. So if we do not have a pedestal defined, then the critical location is going to be d over 2 away from the location of our applied load. So if we didn't have a pedestal here, our applied load would be right here in the center of our footing. And so we'd be d over 2 away from that location. So it can get quite conservative depending on how, large your pedestal is. So that's why if maybe you have like a steel base plate or something, it's good to try to define pedestal plane dimensions when they're applicable to your design.
Perfect. All right. Let's see. Another question: is the soil allowable bearing pressure increase permitted in IBC 2021? If so, do you have a reference to the section, chapter 18? If not, is this permit? Excuse me. If not, is this permitted if recommended by the project's geotechnical engineer? Great question. So, um, some provisions like that are not explicitly based in IBC allowances. Sometimes those are just based off of standard practices often found in geotechnical reports because we want to allow our engineering users to accommodate a wide variety of different project conditions. And so we do have those options if for some reason you have a geotechnical report that says, for every how much you go deeper, you can increase your bearing capacity and so on. Let Chelsea go ahead if you have more thoughts on that. But that's
Yeah.
not an explicitly IBC driven provision. It's a flexibility feature that we provide in case you have a situation where that's called for.
Yeah, I'll just note I've never seen this come through in a geotech report. I've never been given the luxury of some increases in soil bearing pressure, which was why I thought it would be good to like really dive into like what this does and what this means in today's presentation. So yeah, I think that just coordinating with your geotech on that is probably the recommendation.
All right. Question about load linking. Is there a ballpark timeline for adding the linked load feature to wood design? So, as many of you guys know, and we've highlighted in our previous office hours sessions, we do have a survey on the load linking tab where you guys can actually go in and vote about features that you want to see next when you want to see load linking added to other modules. Wood beam to wood beam load linking and wood beam to steel beam load linking is one of our top responses on that survey. And so that's definitely in progress right now. We don't formally announce timelines for things like that because, um, software development is an iterative process and it's hard to predict the exact time where that's going to be available. But we definitely know that that's something people are interested in. It's with the development team making progress right now. Can you clarify your comment about the top rebar mat? Does ENERCALC assume it's there but graphically not display it?
Yes, I can. Let me jump back to that section here. Okay. So, yes, if you see this warning come up, and if you see tension in the top of your footing when you're looking at your bending results, um, ENERCALC is going to assume in the bending check that there is a top mat provided so that it can check that tension in the top of your footing. But we are not currently displaying that reinforcement here. It's we've just said that we're doing that by like showing this note here. And another thing to note, sometimes when people see this note, they think that their design is failing. We can see here that our design is still okay. We just have this note that is reminding us that we do need to provide a top mat in our drawings. And then we also need to check anchor pull out for that tension in the top of the footing.
All right. Going back to the base plate and pedestal questions, if
Mm-hmm.
you're not installing a base plate on a pedestal concrete pier, should we leave the pedestal dimensions as blank?
If you're not installing a base plate on, can you read that again? I'm sorry.
Yeah, so I think they're basically talking about a situation where you're just wanting to design quickly with a concentrated force, but you're not considering actual base plate or pedestal type dimensions, in which case I think you would be simply leaving those inputs blank.
Yeah, if you don't have like a concrete column, a pedestal, um, like a masonry wall or anything that you can like define the plan dimensions, then you can always leave those blank. And then the program's just going to assume that your critical location is going to be that location of the applied load. This would just be conservative if you did, like, for our example, we had a 12-inch square pedestal. And if we ignored that, then we'd see that our critical location, was pushed to an area with higher force. And we would have had a little bit more of a conservative design when we were looking at our our results.
Right.
So
So
we can
fair to
see,
say that the leaving the pedestal dimensions as 0 gives you your most conservative result for punching shear checks.
yeah, yeah, punching shear, yeah. So if you wanted to just do a quick check, it'd be great to leave these blank, and then you'll see that upper limit. But yeah, ACI, there's a table in ACI and it has the location of critical sections for different supporting members. So if you have a supported member in this table, then this is the place that ENERCALC allows you to define those things.
All right, next question. How is the continuous footing under the wall modeled in general footing module? So we will probably have a future office hours session regarding continuous wall footing design. So we're not going to dive into that one today, but definitely feel free to reach out to the support team if you have specific questions or concerns about continuous wall footing um, module questions. Let's see, another question. How well is load linking working? Are folks having smooth use of them? Yeah, I would say if you haven't tried out load linking, you should absolutely get in there and start using it on your projects. Definitely a huge time saver, both on the transcription side, the accuracy side, and then if changes ever happen in your load path, that workflow that Chelsea walked you guys through, where you're able to seamlessly connect one calculation to another, creates durable dynamic relationships between your different load linked calculations. And so if you make a change at the top of that load path, you'll be able to ripple those changes down, update all the reaction forces in real time. So absolutely encourage you guys to start digging into steel beam to steel beam load linking if you haven't tried it yet.
Yeah, I can confidently say it's 100% better than what I used to do, which was write all my calculations down on a piece of paper. And then anytime something changed, I would cross it out and write the new reaction. And yeah, I would have liked to have this when I was in design for sure.
Yeah, for sure. The other cool thing, if you guys haven't played around with load linking yet, the other cool thing about the load linking is like Chelsea was showing on the process of creating the load linked relationship, because you have the array of different ways you can apply those linking relationships. Let's say you have an infill beam and a girder situation where you've got third points or quarter points or some kind of arbitrary spacing. Once you create those load linking relationships, all the controls remain dynamic. And so, let's say you reframe your floor and it goes from third points to quarter points, or it goes from third points to exactly 6 feet on center, or something like that. You can automatically make those changes in real time. It's going to rearrange all your loads and update the calculation. Um, Also dynamic geometry control if your span geometry changes. Let's say you've got a 23-foot span loaded at third points, all of a sudden that becomes a 36-foot span. You're still going to have third point loads. Everything's going to modify dynamically on the fly. So definitely encourage you guys to dig into that. Speaking of load linking, follow-up question from Mike. Do you get indications of members changing after you change something higher in the load path? Absolutely.
Mhm.
If Chelsea jumps back to the status badges, you can go ahead and dig into his question if you want.
Yeah, so let's say for example, like I'm gonna change something in my transfer girder number one. This is providing reactions to my transfer girder number two, and it's receiving reactions from my primary girder above it. So if I made a change here, I would see that like my upstream beams, they don't change. Both of these status badges would remain green, but I would see that here, this transfer girder number two, that status badge would change to orange, and it would indicate to me that this calculation is not up to date. There are some loads being applied from the linked reactions that are not current. And I can either come in and open this calc up and the program will communicate, to update that, or I can come up and I can recalculate. I can bulk recalculate up here. If I have like, 10 calculations that got updated, instead of opening each one individually, I can go and recalculate here. And if you guys are, I'm excited to hear that you guys are really interested about load linking, where it's a feature that we're really proud of and we're excited for you all to use. We're happy to answer any more questions here today, but also if you wanted to check out the status badges, they're explained really well in this video on our YouTube page. There's a quick like walkthrough tutorial here. I think the runtime on this is, about like 26-ish minutes. And, after you watch this, you'll be locked and loaded, ready to use this feature.
All right. Question from Miguel. If I'm bringing the combined loads from another program like Reza 3D, how should I incorporate the loads, taking into account that they have already been factored? So when you're
Huh.
working with another program that's performing analysis and then you want to be able to go into foundation design, it's highly advisable that you try to output those reactions on a case by case basis from your analysis software so that you can feed those directly into the case by case input fields,
Mhm.
because all of those input fields are set up to use unfactored case by case inputs. It's conceivable you could customize your load combination sets if you wanted to build something that lets you feed seamlessly from raw outputs from another program, but you just want to be aware that the ENERCALC interface is explicitly set up to take case by case inputs. Let's see. Another question about applied loads.
Mhm.
A shear load applied at the top of the pedestal, the additional moment is taken to the top of the footing and not to the bottom of the footing. So, kind of another clarifying question about the nature of those applied loads. Chelsea, feel free to jump on that if you have thoughts about those applied loads. The diagrams you have up right now probably help answer that as well.
Yeah, so that additional moment that we're going to see from our shear load, it's going to be applied at the top of our footing. And then all of our calculations are run assuming that, all these reactions are happening at the top of our footing.
Yeah, and for moment in particular, an externally applied moment that you specify
Uh-huh.
is just going to be a global stability moment on the footing itself. Globally, it's not specific to top face, bottom face, and so on. Hopefully that covers that question. All right, let's see here. We are just a little bit after the end of the hour. Still a few more questions. We'll get one or two more, and then we're going to go ahead and wrap it up here. Can you discuss the overturning and sliding settings on the general tab more? Using 1.0 seems like you would have no factor of safety for overturning.
Sure. Let me pop that open here. I'll just open this general tab. Okay, so yes, I believe from my research that this is a hotly debated topic. You can update these to be whatever you feel they need to be using your engineering judgment or in discussions with your geotech. So 1.5 is another common factor of safety that we'll see here. There is an argument to be made that because the load combinations have some factor safety built into them, that maybe 1.0 is sufficient. But ENERCALC's goal is never to tell the engineer how to apply their judgment or how to interpret the code. We always just want to provide you with as much flexibility in our modules to apply whatever judgment you need to, and to use our modules in the way that serves you and your project. So if you would prefer a 1.5 factor safety here, you can go ahead and do that. You can also make that your default. So every new calculation has that factor of safety. This was just what I chose for the example. Maybe not what I would choose in a real life project, but yeah.
All right. Well, I think with that, we're going to go ahead and wrap it up for today. If there was any question that we didn't get answered, or if there's something that needs a deeper dive, we always encourage you guys to reach out to the support team and follow up with our structural engineering team about those things. We absolutely want to get those questions answered for you guys. Before we go ahead and say goodbye for this session, we'll go ahead and let Chelsea kind of wrap us up with some final thoughts and a teaser for next month's session.
Cool. Well, thanks everyone for your time today. We really appreciate you being here. I had fun presenting to you guys. I hope that you had a little bit of fun listening to me. Um, Next month, we're going to focus on the concrete beam module. So we hope that you'll join us for that office hour session on January 8th. And we hope that you guys all have a wonderful end to your 2024, and we'll see you next year.
All right. Thank you guys very much for being here. We always look forward to seeing everybody for our monthly office hours sessions. Don't forget to sign up to get reminded for next month, and we'll look forward to seeing you guys in January to talk about concrete beam.